Here, chapter 15. So we've been talking about solutions, and more importantly, we've been talking about molarity, which is our moles per liter or moles of solute per liter of solution. And remember that molarity basically can act as a formula. So we do solve for any of these three things. So liters is moles divided by molarity, and moles, which is a very common conversion, is liters times molarity. Remember that when you are using volume and molarity together, you want to make sure that your volume is in liters so that things cancel out correctly. Again, if you multiply milliliters by molarity, you are not going to get moles. You'll get millimoles, which you'll be off by a factor of 1,000, which in most cases you want moles. So always make sure that it is in liters here. Also remember that if we do have something given to us with the molarity sort of symbol there, it's oftentimes good to convert it into a usable sort of conversion factor where you actually see both of those units in the problem, so you can set it up with dimensional analysis. Again, as we talked about a number of times, a very common mistake people make is they will keep that big M in the calculation, and before you know it, they have no idea about the volume part of it. All they think about is the moles part of it, and they end up doing the calculation incorrectly. Now, we also talked about dilution at the end there. And dilution is really when we add more solvent to our solution. So that is going to be our moles of solute over our liters of solution. Remember that a solution is both the solute and the solvent together. So when we do a dilution, we do see that the molarity does decrease. And the molarity decreases because the only thing that we're adding basically is more solvent. And that will make our denominator larger and our molarity will go down. Remember that also we have a formula that goes with dilution, which is M1V1 equals M2V2. And that is usually the more concentrated solution. This is the more dilute solution. And usually if you solve for V1, that's how much of the more concentrated solution you need. V2 is your final volume. So very often in these problems, they want to know how much solvent or water you added. So usually taking V2 minus V1 will give you how much of that water that you added. This is okay in this equation, as we talked about, to use milliliters, bless you, for both of the volumes, and that's because the units will cancel out correctly. But you should always use liters when you are using molarity and volume by itself, not in a dilution situation. A kind of more generic version of this equation, which is C1V1 equals C2V2, where it's just concentration for both of those guys and volumes. That's because we could really use this equation for any type of concentration unit, like percent mass, percent mass volume, etc. But most commonly molarity is used, so a lot of times we use M1V1 equals M2V2. Okay, let's take a look at this one here. What is the volume of 19 molar sodium hydroxide? It needs to be prepared from 1 liter of 0.115, 0.15 sodium hydroxide. So obviously it is sodium hydroxide and sodium hydroxide, so there's no reaction happening. So what we've basically got going on here is 19 molar bottle of sodium hydroxide, which is more concentrated. We are looking to make 1 liter of this solution. That's basically 1,000 milliliters. It wants to be a molarity of 0.15 molar. So again, this is a dilution type situation. So we could use our M1 V1 equals M2 V2 in this situation. We could label this as M1. Thank you. This could be V2, and this could be M2 in this case. So really the only thing that we are missing is V1, which is really the volume that we need to take out of the more concentrated solution. So we're going to divide the M1 to the other side. Will give us V1 is equal to M2 V2 and M1. Putting in our values here, 0.15 molar. our 1 liter. And on this side, we have 19 molar. So our molarities cancel in this case. And we end up with basically 0.0079 liters of sodium hydroxide, or that's approximately 7.9 milliliters of sodium hydroxide. Any questions on that calculation? So what does that number represent? That number represents how much of the more concentrated solution that you would take out. That means that if I wanted to make my new solution here, should I put 1,000 milliliters of water in this case? I should not, right? Because then I'd have something like 1,007 milliliters of solution, which is too much. We want to end at 1,000 milliliters, or 1 liter in this case. So again, to figure out how much water, we could take our V2 minus our V1. So this would be 1,000. I'm just going to do it in milliliters, minus 7.9 milliliters, going to get us about 992.1 milliliters of water. So to that 7.9 that I already put in there, I would need to put 992.1 milliliters of water. That would give me a total volume of 1 liter, or 1,000 milliliters. And at that point, if you mix it up really good, you should have a solution that's sitting there at 0.15 molar. Any questions on how to make that solution there? All right, let's try the next one here that we got going. How much water is needed to prepare 500 milliliters of 0.25 molar calcium nitrate from a 5 molar calcium nitrate solution? Okay, so let's take a look at this one. We have a more concentrated solution here, calcium nitrate, that is 5 molar. We want to make a new solution that has a volume of 500 milliliters and a molarity there of 0.25 molar. So once again, I'm going to make our more concentrated one, the ones. We're going to be looking for V1 as we don't have it. We'll call these guys 2. So here again, M1 V1 equals M2 V2. Once again, dividing that to the other side. As I mentioned previously, this is a situation where if you want, you can leave the volume in milliliters. You do not need to convert it to liters. If you want to convert it to liters, you can. So V1 is equal to 0.250 molar and 500 milliliters divided by our 5 molar. So this is why, again, you can leave it in milliliters, because the molarities will cancel out and you'll be left with milliliters in this case. Once again, though, if you're not using the dilution equation, you do need to make sure that you convert it to liters, so you do end up with the correct units, of which are moles. You could also convert it to liters here if you want to. The only difference is obviously your answer would be in liters rather than milliliters. So in this case, we will end up with 25 milliliters. Once again, though, in this case, that 25 milliliters is really our V1, which is what we're going to take out of this first more concentrated solution and put it into our second solution. And that means that in this case, we did want to actually know how much water we're going to add. So we do need to take, in this case, our V2 minus our V1. That will give us our 500 milliliters minus the 25 we put in there. Means we need something like 475 milliliters of water needs to be added to that. So we would top that off with 475 milliliters, giving us our grand total there of 500 milliliters. And our M2, after we would mix it, would be 0.25. Questions on that there? Yeah. Yeah. So usually in most cases, the more concentrated numbers are the ones and the diluted solution is the twos. It really doesn't matter as long as truthfully you keep the numbers that go together. So in this case, if you calculated it as V1 and M1, what's the 500 and 0.2, you'll get the same answer, obviously. So as long as you technically keep them together, you'll be okay. But typically speaking, usually the ones are the more concentrated and the more dilute are the twos in that particular case. Yeah. It does in this case. So in this example, it didn't ask for it in milliliters or liters. So either one would have been okay. Yeah, so up to that point before we did it here, we were basically multiplying and dividing, and the smallest there is really 3, and that gave us 3, which really took us to 1 decimal place. And then when we subtracted here, we would still keep it to 1 decimal place at that point, which is our last sort of step. Yeah. Other questions? Also, a reminder that this equation is really for dilutions only, and you really shouldn't use it for things like titrations or solution stoichiometry. It won't work in all cases. It will work in a couple of cases where you get lucky. But for any type of solution stoichiometry like titrations and stuff that you did the other day in lab, you should be doing stoichiometry problem, not just plugging it into this equation, because you will get it wrong in a lot of cases. But if it's not a one-to-one relationship between the acid and base, you will not get it correct. So you should really just use this equation, as I might have mentioned last time, as the dilution equation. Even though if you look online, sometimes people call it the titration equation. But you should only really use it for dilutions. Any questions on that there? All right, so speaking of stoichiometry, let's talk about solution stoichiometry and some different types of solution stoichiometry problems. So solution stoichiometry problems are pretty much like all other stoichiometry problems. Really, the only difference is a lot of times how we get to moles. And at the end, instead of maybe calculating grams or something like that, which you might still do, we may look for something like molarity. We may look for the volume of solution or something of that nature. So it's really those same sort of 4 steps. You still want to balance the equation. You want to convert to moles. And again, in a lot of cases, you will use this relationship, which obviously that is the molarity there times the volume to get to moles. And just like we've been talking about, pretty much any type of stoichiometry problem, you do want to make sure that it is not a limiting reagent problem, or if it is a limiting reagent problem, you do need to figure out which one's the limiting reagent. And by the way, you do need to figure that out through some sort of calculation, not just picking the smaller number. So you do have to do a calculation to figure out which one's the limiting reagent. It's not always the smallest number. So you would do the same sort of way that we talked about previously, either figure out how much of one reagent you need to use up the other, or figure out how much product each one sort of makes. And the smallest one would be your limiting reagent and your theoretical yield. Now, if it happens to be that, obviously you'd want to continue on with your limiting reagent problem. If it's not, then you would just continue on with obviously with what was given to you. How you know, again, it is a limiting reagent problem is you have enough information given to you that you could get to moles of each of the reactants. So that is how you know it is actually a limiting reagent type problem. Once you do that, you're going to do the mole-to-mole relationship, which is our normal 3rd step. And again, here at the end, 1 or 2 things oftentimes are sort of used. We may do moles and liters to get to the molarity. We may be looking for liters using the moles and the molarity given to us. And we may just do a regular stoichiometry move, take moles to grams like we've done before, which would use the molar mass from the periodic table. So let's take a look at one here and sort of see how it goes. We'll do it here together and go through it. We want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of 0.2 molar barium nitrate to precipitate everybody in the form of barium sulfate. We also want to calculate the mass of barium sulfate. So clearly, as we know, any type of stoichiometry problem, regardless of the type, the first thing that you need is an equation. So that's what we want to start with. And since we have everything in words, a reminder that we do want to just start with the correct formulas first to make sure that we have those before we get to the balancing part. So we want to know sodium sulfate. So sodium is +1, sulfate is -2, which means when you put that together, you get a little sodium sulfate, which I guess in this case is a solid. And we're going to react it with barium nitrate. Barium is +2, nitrate is -1, which means when we put it together, we end up with something like this. So just looking at that, you should also recognize that as a double displacement reaction. And that means that our positive guys are going to switch partners. Also really important when you do that, that you put together the formulas on the right-hand side of the arrow correctly. Again, not worrying about the balancing part of it. So sodium is +1, nitrate is -1. That gives us NaNO3. And that would be aqueous based on our solubility rules. Barium is +2 and sulfate is -2, which means when they come together, once again, that is the proper formula that you should end up with. As you saw there, and as we talked about previously, we're not concerned about the balancing aspect of it until you get down all of the proper formulas. Now you do need to go back and do some balancing. And it looks like perhaps in this case, we just need a 2 right about there. And I think everything else here will be balanced. Any questions on how we got to the formula in this case? Now we got the formula, we can really analyze sort of what is given to us. So we have 250 milliliters of this guy, which is 0.2. And again, I'm going to get rid of the big M and convert it into moles per liter, which is a good thing to do. And in this case, we're looking for the grams of our sodium sulfate, and we're also looking for our grams of our barium nitrate. So we're actually looking for two things in this problem. It doesn't really matter. We could take each of them separately. In this case, we also know it's not a limiting reagent problem because we could only get to moles of the one reactant, and we're also looking for the other reactant. So clearly it can't be a limiting reagent problem in this case because we can't get to moles of each of them. But we definitely could get to moles of these guys here. So that is where we want to start. And a reminder that we do need to convert our milliliters into liters since we're using it here with our molarity. And that would convert it into 0.2500 liters. So starting with that, I'm going to take my 0.2500 liters of barium nitrate. I'm going to use the molarity and dimensional analysis here so I can see the moles and the liters part. The liters here of barium nitrate are going to cancel out, and that will get me at this point 0.05 moles of barium nitrate. So far, basically step number 1 and step number 2 there, converting to moles. Again, instead of using molar mass and the grams, we're using our volume and molarity. Any questions up to there? At this point, you do have two ways you could go. You could go from our barium nitrate to our sodium sulfate, and we could also just go that way first. So in this case, I'm actually going to go to the sodium sulfate first and figure that out. So I'm just going to get some places to write. So the first one I'm going to look at is the relationship of the barium nitrate to the sodium sulfate. And what we can see from there is for every 1 mole of sodium sulfate, I get 1 mole of the barium nitrate. So at this point, we will pick up with our moles of our barium nitrate. We will use the stoichiometry from the equation. 1 mole of barium nitrate gives us 1 mole of our sodium sulfate. If I stop right at this point, The moles of barium nitrate cancel. I am left with moles of sodium sulfate, but I am looking for how many grams that is. So again, we do need to go to the periodic table. And for sodium sulfate, that would be 2 times 2299 for our sodium, plus 3207 for our sulfur, plus 4 times 16. That gives us something like 142.1 grams per mole as the molar mass. And that's what we're going to use here as our last step. We're going to go from moles to grams. So we do want the grams up on top of 142.1 grams per mole of sodium sulfate. The moles will cancel. Gets us 0.05 times 142.1. Going to get us something like 7.11 grams of sodium sulfate would be needed in this example to mix with the 250 milliliters of our barium nitrate. Any question on those steps there? So obviously for that part of the problem, that would be step number 3, mole-to-mole relationship, and step number 4 there. Again, kind of traditional, using the molar mass to figure out the grams. Yeah. You really don't on your calculator, you mean? No, you really you can't. It's like, obviously you don't need to multiply by the 1 or divide by the 1. It's just going to be 1 anyways. It'll come out the same. Yeah. Yeah. You wouldn't use that in this case because this is not a gas. So that 22.4 is for gases at standard temperature and pressure. So this is just a milliliter to liter conversion, or a milli sort of conversion, which is 1,000 into 1 liter. And that's a conversion you use a lot with molarity, because oftentimes, as you could probably see in lab, most of the time you take your volume readings in milliliters. So converting milliliters to liters is a very common sort of conversion. Yeah. But definitely you don't want to use that one because that's specifically for gas and more specifically for standard temperature and pressure sort of situations. Other questions? All right, at this point, we also can figure out the other part of the question, which was how much of the barium sulfate we would actually produce in this case. So we would look at our relationship here between our barium nitrate and our barium sulfate. And not bad, also 1-to-1, so that's not too bad. So 1 mole of barium nitrate, they obviously will not always be 1 mole, equals 1 mole of barium sulfate. So really, we could pick it up in a couple of spots, but since we have this number here, might as well just start with that number again. So we're going to take our 0.05 moles of barium nitrate. Going to use our mole-to-mole relationship here from the equation. 1 mole of barium nitrate equals 1 mole of barium sulfate. And once again, you could get an answer if you wanted it in moles, but we do want grams again. So back to the periodic table here to calculate the molar mass. So barium here, what is that barium? 137.3. $32.07 for our sulfur, plus 4 times 16 for our oxygen. Going to give us 233.4. That's for our barium sulfate. So using that as our conversion factor, once again, we do want to end up with grams, so we'll put the grams up on top. Moles of barium sulfate cancel, and that will get us 0.05 times 233.4. Going to give us 11.7 grams of barium sulfate would be produced. That would be a theoretical yield in this case, since that is a product, right? Any questions on that? Obviously, as well, if perhaps you did get an answer for the moles for this guy, you could have just picked it up with that and went over to the product as well. Again, it will all work out the same. Question on any of those steps. Again, same 4 steps here, finishing down our 4 steps for this part of the problem, 3rd step and 4th step in this case. Any questions on any of that there? All right, so I tried one. Once you try one here and see what you come up with. Calculate the mass of calcium carbonate that forms when 25 milliliters of 0.1 molar calcium nitrate mixes with 20 milliliters of 0.15 sodium carbonate. Let me give you some numbers that might be helpful. Calcium 4008, carbon 12.01, oxygen 16. Okay, so let's take a look, see how you're doing. So once again, obviously we were dealing with a stoichiometry problem and we don't have the equation. So always we want to start with that. We want to calculate the mass of white solid calcium carbonate that forms. So obviously that is a product when we react our calcium nitrate with our sodium carbonate. And we know these are solutions, and based on solubility rules, they should be aqueous. Once again, if you're not sure, this should also look very familiar to you as a double displacement reaction. So again, we're just going to swap our partners. And again, we want to make sure we have the right formula. So they gave you one of them. So hopefully you can't screw that up, hopefully. And that's going to be a solid. That means our sodium and our nitrate are going to come together. And remember, sodium is +1, nitrate's -1, which means we do end up with NaNO3, which would be aqueous. We again do not end up with Na2NO3 Like, you want to put it together without the balancing component. And now that we do have the right formulas, now we want to go back again here and balance everything. Get some of this stuff out of the way. And it looks like in this case, we're going to need some 2s as well, I think. So maybe just a 2 there, and I think we're okay. Any questions on how to get to the equation here? At this point, we can look at what was given to us, and we have 25 milliliters of this guy. That is 0.1 moles per liter. Again, I'm getting rid of the big M for my calculation. Also have 20 milliliters of our sodium carbonate. That is 0.15 moles per liter. So by looking at the information given to us, you should recognize that this is a limiting reagent problem, as you have the moles of each of them, or you could get to the moles of each of them. So you do have to do that limiting reagent step, which again is a calculation, not just the smallest number. So that's where we want to start, really, is we got the equation. We might as well convert these guys into moles. So we got our equation. We're going to convert into moles. We do have to convert our volumes into liters. So just like we did on the previous problem, we're going to divide by 1,000. And that'll give us 0.025 liters. And similarly there for our 20, we'll get something very similar. So 0.0250 liters of our calcium nitrate. Using the molarity like it is, because the liters will cancel, will give us our moles of calcium nitrate. So 0.025 times 0.1, 0.0025. We'll do the same thing for our other reactant. And by converting into liters, we're going to divide this guy by 1,000. And that will be our sodium carbonate. Using the molarity of our sodium carbonate, which is 0.15 moles per liter. Again, the liters will cancel, and that's going to get us 0.003 moles of sodium carbonate. So this again is our starting amount of each of these. And once again, we'd go to 3 significant figures based off of really the volume and the molarity in each of these cases. Instead of using grams of molar mass to get the moles, again, volume and molarity to do so. Any questions up to there? Once again, you do have to do some type of calculation to figure out the limiting reagent. So I'm going to do the one like we talked about, which is I'm going to try to figure out how much of one reagent I need to use up the other. So in my case, I'm going to choose the calcium nitrate. I'm going to take the moles of calcium nitrate that I'm starting with. And I'm going to do a mole-to-mole relationship between my 2 reactants, which again happens to be a 1-to-1 in this case. The moles cancel. That means 0.0025 moles of sodium carbonate is needed in this case. What I want to do is compare that to my starting amount of sodium carbonate, and I do have enough. So I need 0.0025, and I am starting with 0.003 moles of it. I have enough, and what that tells us is that this here would be our excess reagent, and that would be our limiting reagent. Relations to the product, and whichever one is the smaller amount of product. Any questions on that? Okay, so again, you can't just choose the smallest number. So now that I know which one's my limiting reagent, I can now finish the calculation. I want to start with the starting amount of my limiting reagent, because that's how much product I'm going to produce. 0.00250 moles of calcium nitrate. We're going to do a mole-to-mole relationship between the calcium nitrate in this case and our product. And that is a 1 mole of calcium nitrate to 1 mole of calcium carbonate. And in this case, we do want how many grams. So we do have to go to the molar periodic table to get the molar mass. And for calcium carbonate, that is 4008 for our calcium, plus 1201 for our carbon, plus 3 times 16. And that's going to get us 4008 plus 12.01 plus 3 times 16. 100.1 grams per mole. So we'll use that as our last little step here. We're going to put the grams up on top so we end up with grams. And we will end up with 0.00, too many zeros, 0.0025 times 100.1. It's like we end up with 0.250 grams of calcium carbonate. This again would be a theoretical yield, as that's how much product we produced. Once again, limiting reagent, and then steps 3 and 4 in our calculation. Yeah. Any questions on that one? So we've done stoichiometry involving solutions, gases, regular stoichiometry. Again, you always want to make sure that it is not or is a limiting reagent problem. So you don't want to overlook that part of it. And again, a reminder, you got to do some type of calculation to show which one is a limiting reagent. Any questions on that type of stoichiometry? All right, then let's talk about some more stoichiometry here. And similar to what you did last week in lab, where you did titrations. So acid and base titrations is a common solution stoichiometry sort of event that we do. If you remember when you did your titrations, you got to your equivalence point where it turned pink, maybe dark pink if you put one drop too many even. But somewhere along the way, you get to your equivalence point. And in a titration, we oftentimes do a titration when we have sort of a known solution and an unknown solution. So, for example, in your titrations you did last week, the hydrochloric was your unknown solution. About it. So you use basically the sodium hydroxide's information and stoichiometry to figure out what was going on with the hydrochloric acid. Same thing with your acetic acid or unknown or whichever one you had there on your second titration. So a lot of times these acid-based ones, when we reach the equivalence point, they are neutralized because you have equal amounts of acid and base that have been added to each other. And overall, what happens when you take a strong acid and strong base, you always get a strong acid plus a strong base will always get you water and a salt, and a salt's an ionic compound. And if you remember when we were talking about types of reactions, pretty much any combination of strong acid and strong base, if you go to the net ionic equation, pretty much that's what's happening there. You're going to make water, which is one of the reasons why a reaction takes place. The H plus from the acid, the OH minus from the base is basically what's coming together there to make water. So these are also, again, really solution stoichiometry problems. So let's take a look at one here. What volume of 0.15 molar nitric acid is needed to neutralize 45 milliliters of 0.55 molar KOH? So once again, this is sort of like a titration situation where we talk about neutralizing. So if we work this one here together, we're going to take our acid, which is our nitric acid, which is a strong acid, and we're going to react it with our base. And if you remember, acid-base reaction basically falls under double displacement reaction is essentially what is happening here. So we have our positive negative guy, our positive negative. So that is where water comes from when the H plus and the OH comes together. And then the K and the NO3 come together. And that's going to give us, once again, our water and our salts. So our K is K plus, and our nitrate is NO3 minus. So when that comes together, we get, again, our water and our salt in this case. Any questions on how we get to that reaction there? And again, always pretty much H and OH to make the water there from our acid and our base. So if we look at the information given to us, we are looking for the volume here of our acid. We do know the molarity is 0.15 moles per liter. For our base, it is 45 milliliters and 0.55 moles per liter. Once again, it is a basic stoichiometry problem as we are looking for the other reactant, so it can't be a limiting reagent problem. But we can start with where we could get to moles, and that is our potassium hydroxide. So we do need to convert our milliliters into liters. So we'll do our conversion here. Basically moving our decimal place 3 places there to the left. And we will start with 0.045 liters of KOH. Using the mole to mole relationship between the nitric acid and the KOH. And once again, it won't always be 1-to-1. Happens we have a big run of 1-to-1s here. 3. So the moles of our KOH is going to cancel. But before I do that, I should get the moles first. So let me try that again. Before I jump to that step, let's actually use the molarity, which was given to us, which is 0.55 moles per liter of KOH. Now the liters will cancel, and that'll give us 0.045 times 0.550, 0.0248 moles of KOH. Now that we have the moles of KOH, again, we really need the moles of our nitric acid, because if we look at the molarity of our nitric acid, we're looking for the volume. We have the molarity, so we do need to use stoichiometry to get to the moles so that we can get to the liters. So now we'll use our one-to-one relationship. 1 mole of KOH is 1 mole of HNO3. The moles will cancel. 0.0248 moles of nitric acid. So up front here, really a basic stoichiometry problem: balance the equation, convert to moles, mole to mole relationship. So here's where we'll also vary a little bit. We're not going to look for grams in this case, but since we do have the molarity and now we have the moles of our nitric acid, we could use that to figure out our volume. And our volume would be liters is equal to moles divided by molarity. So taking our moles, using the molarity of nitric acid, which is right here, 0. The moles are going to will get us 0.0248 divided by 0.150, about 0.165 liters of nitric acid. And again, they didn't really ask for any specific unit. So if you wanted to convert it like the other unit into 165 milliliters, you could as well in this particular case. So that would be step number 4. Again, a little bit different what we were just doing. We can use molar mass, but at the back end here, we again use the concentration and our moles to get to the volume, which again is a very common sort of thing. Any questions on any of those steps there? Yeah. So you should always show a stoichiometry problem like this. You use the stoichiometry steps and the balance equation and all that. So the answer is, will you get the same answer? The answer is yes. And you only get the same answer because it's a one-to-one relationship between the acid and base. But it will not always be a one-to-one relationship between the acid and base, which means if you throw it into there blindly, you'll get the wrong answer more times than not. So you really should only use M1V1 equals M2V2 for dilutions. Again, some people call it the titration information equation, but it's specific for this type of situation where the acid and base is one-to-one. And if you do that later on down the road in other classes, they will not give you credit for it. Yeah, they expect you to write the equation, they expect you to show the mole-to-mole relationship, and they expect you to do a stoichiometry, and not that way. So again, it will work, but only for that specific type of titration where it's a one-to-one relationship. Other questions on that? So my advice is just keep it for dilutions, which is really what it should be kind of used for. Other questions? Yeah. All right, so why don't you try this one here? What volume? I think it was missing on your notes there. A 0.355 molar sodium hydroxide is required to react with 125 milliliters of sulfuric acid. Okay, let's take a look. So obviously we're doing a titration here. We want to start with the equation. So sulfuric acid is H2SO4 plus our sodium hydroxide, which is NaOH. Once again, this is an acid base or double displacement reaction, however you want to think about it. But if you think about it as an acid and base, you know you definitely should get water as a result. And that's going to come from really our hydrogen and our OH coming together as they switch partners. That also means the sodium here and the sulfate will switch partners. And once again, you want to make sure you get the right formula. Sodium being +1 and sulfate being -2, which means that you should end up with a Na2SO4 that is happening there. Any questions on that there? We do want to balance it here. So to balance it, looks like we will need a 2 right about there and probably a 2 right about there as well. Any questions on how to get to the equation? Once again, acid and base, so you have your water and your salt, basically, in this case. At this point, we can look at the information given to us. We are looking for the volume of sodium hydroxide, so we're looking for the volume. And we do have the molarity of 0.55 moles per liter. For our sulfuric acid, we have 125 milliliters and a molarity of 0.5 moles per liter. Once again, this is not a limiting reagent problem as we are looking for another reactant, so obviously it can't be, and it's really just this piece of information here that we could get to moles. So that's really where we want to start. We want to get to moles. Before we do that, we do have to convert our volume into liters. So once again, dividing by 1,000 will give us 0.125 liters of our sulfuric acid. Using the molarity of our sulfuric acid to convert it into moles, we're going to multiply by the moles per liter. Those guys will cancel, and that will get us 0.125 times 0.5, 0.0625 moles of our sulfuric acid. So that's again sort of step number one. Step number two. Step number three is going to be our mole to mole relationship, in this case between sodium hydroxide and our sulfuric acid. And we can see from the equation 1 mole of the sulfuric acid will give us 2 moles of the sodium hydroxide. So continuing on here to convert it into our sodium hydroxide, which is what we need to complete the problem. 1 mole of sulfuric acid, 2 moles of sodium hydroxide. So those guys are going to cancel and times that by 2, 0.125 moles of sodium hydroxide. And that would be obviously step number 3 here. Question? Yeah. Yeah, you could continue on with the calculation if you want. So as long as it's set up that you can see the units canceling and continue on, you can do that. Yeah. Other questions? So at this point, we now have, when we think about the molarity of the sodium hydroxide, we have now the moles from the stoichiometry. We have the molarity given to us. So now we do have everything that we need to get to the volume. So our liters in this case would be our moles divided by our molarity. So taking our moles, 0.125 moles of sodium hydroxide, and using the molarity, 0.3, the bottom there, 0.355 moles per liter of sodium hydroxide, so that the moles cancel, gets us 0.352 liters of sodium hydroxide, or 352 milliliters of sodium hydroxide. And that obviously would be step number 4 there, instead of using our molar mass in that case. Any questions on any of those steps there? So this would be a problem where, as the question was about the M1V1 equals M2V2, here you'd be half the way there, yes, because it's a 1-to-2 relationship versus a 1-to-1 relationship. So you should always obviously do it as a stoichiometry problem and not just plug and chug into that equation, because you will not have the right mole-to-mole relationship. Yeah.
Would you rather us write like both the liters and milliliters?
No, like I said, as I think an earlier question, in this case, you could leave it at either one. Probably most of the time, in this particular problem, you would probably want to leave your volume unit the same as the other volume unit. So since this other one was milliliters, probably most of the time people would probably convert to milliliters. But technically speaking, since it really didn't specify any volume unit, is good to go. Yeah, yeah. Should only really be used for dilution. So that's the only place I would pull it out for, is when you're doing some type of dilution. And these are not dilutions. These are basically reactions that are happening. So like those earlier problems where we did dilutions, where it was like you had 19 molar sodium hydroxide and you want to make like a 5 molar sodium hydroxide. It's sodium hydroxide. All you're really doing is adding more water in that case, or like the calcium nitrate one. So that is really, I would highly recommend, that's probably the only time you should use it. Later on, when you take some more chemistry classes, when you add volumes together and you want to figure out what the molarity is of like the mixed solution, that's also a dilution situation where you can use it. But you shouldn't really not use it for titrations. Again, sometimes people tell you to use it for titrations, but it really is only useful for a very specific type of titration. And they would probably want to see even that type shown, more of a stoichiometry problem. So strictly only a dilution where basically just adding water, mixing two solutions together to figure out a molarity of a combined solution. Other than that, it should be more of a stoichiometry. And really the M1V1 equals M2V2 is a shortcut calculation of stoichiometry. When you do that type of thing, it's really just a shortcut calculation for this. And again, it only works because it's a one-to-one relationship. Other questions on that? All right. I think we will lay it up there for